Hello and welcome you all for today's fourth lecture on the subject thermal engineering. We have already seen three lectures on this first topic, that is fundamentals of thermodynamics. So today we will continue with the same chapter. I would like to request everyone to please go through the first three lectures because whatever the contents we have discussed in those three lectures, those are very important for the understanding of all the concepts which we are going to study from here afterwards. So just go through all those lectures and then you should attend this fourth lecture. Now we will just take a review of what we have studied in the third lecture. So in the third lecture, we have started with the concept of heat and work. So there we have studied the definition of for heat as well as for work. We have also seen the sign conventions already. We have seen the difference between heat and work. The main important part that I have told that you should remember which one is called as high grade energy and low grade energy. So work is usually called as high grade energy since it can be totally converted into heat, whereas heat is called as a low grade energy because we cannot convert 100% heat into a equivalent amount of work. Then again, after heat and work, we have seen what is energy. We have also seen its types, that is potential energy, its definition along with example. Then we have also seen what is kinetic energy along with its example. After studying the concept of potential energy and kinetic energy, we have seen what is internal energy. Then again, after internal energy, we have seen the concept of enthalpy. So as earlier, I have told that the concept of enthalpy is very important in thermodynamics because it gives information that how much amount of heat is available in the system and whether that heat is sufficient to produce any work or not. Because many times students have or they get confused in between heat and enthalpy. So you should now must have understood the difference between this heat and enthalpy. Then again, after enthalpy, we have seen the concept of entropy, that is nothing but randomness or disordered molecular motion. So in case of solid, liquid and gases, we have already studied how the entropy will change. So these were the all points which we have studied in the previous lecture. Now we will start with the further points from this chapter. We will start with the concept of flow work. This point is very important because in many papers this question has been asked. So the flow work is also called as a flow energy. It is related with the flow process. You should know that the flow work or flow energy is the concept which is only related to open system. We have already studied various types of systems such as open system, closed system, or isolated system. However, you should remember that in case of closed system and isolated system, I have told you that there will be no any exchange of mass. In case of the closed system, there is only transfer of energy. However, mass is not transferred, and whereas in case of isolated system, there is neither transfer of mass nor transfer of energy. So for flow work, it is necessary that there should be exchange of mass in between the system and surrounding. So this concept of flow work, it is only applicable to open system. So this point you should always remember. Now if we see the definition of flow work, then flow work is defined as the work required to cause the flow of fluid in any passage. Or in other words, we can say that it represents the work necessary to advance a fluid against the existing pressure. Now to understand this concept of flow work, we will consider an example. A diagram has been given here. So we will just consider that a cylinder with control volume CV is given, which is as shown in figure by the letter CV. So this will be our system, and near to this CV, we can see a dotted line. So this dotted line, it is nothing but the boundary of that system. This system is also having an inlet and outlet section arrangement, which are shown in figure. At these sections, we are having piston arrangement. Also, the pink color, which is shown in the figure, it represents the presence of fluid element in the system. Now, if we want to push the entire fluid into the control volume, which is represented as CV in diagram, then some force should be applied to the inlet piston. So let us assume that due to this force F, the piston is displaced by some length, say capital L. Thus, if we want to calculate the work done in pushing this fluid element across the boundary, then we can calculate that by using formula W is equal to F into L. We have already studied in the definition of work. We call it as it is nothing but the product of force and displacement. So here, since the force is F and the displacement is L, we can take flow work equal to force product of force and length, that is F into L. But we also know that pressure is nothing but force per unit area, so we can write force as the product of pressure and area. So in the formula of flow work, we can just replace F by P and E. So we will get the formula for flow work as P into A into L. Now again, the product of A and L, that is area and length, it is nothing but volume. So again, the formula will get modified as follows, that is flow work is equal to P into V. So the product of this pressure and specific volume, it is nothing but the flow work. So we can define the flow work in this way. From this concept of flow work, we should understand that when mass of fluid enters into a system, then work must be done on the system. And in a similar fashion, when mass leaves the boundary of the system, then flow work must be done on the environment or surrounding. So this was all about the concept of flow work. Now we will study the most important part from this chapter, that is laws of thermodynamics. So there are total 3 laws of thermodynamics which we have to study. All these laws are very important from exam point of view, because in almost every paper either one of the law is compulsory asked in the paper. So we will see all these laws one by one. We will first start with zeroth law of thermodynamics. Then we will see the law of conservation of energy. Then first law of thermodynamics, and finally the second law of thermodynamics. Zeroth law of thermodynamics. The name itself creates some doubt in the minds of students, because students usually ask that why this name, that is zeroth law, is given, because instead just like first law, second law, some another name might have given for this law, say as third law of thermodynamics or fourth or fifth law of thermodynamics. Then to know why this zeroth law of thermodynamics name is given, we should know what is the history for this law. So the answer to this question is very much interesting or surprising, because in the year 1824, the second law was first stated by the scientist Sadi Carnot, who was studying on the working of steam engine. Though the second law of thermodynamics was stated, it was necessary that the foundation of second law of thermodynamics, some another law, should be explained, which was related to the conservation of energy. And so the first law of thermodynamics came into existence in the year 1848, which was given by the scientist two scientists, that is Herman and William Thomson. Then again, after some more years, that is in the year 1931, another scientist named as Fowler, he realized that before explaining the first law of thermodynamics, it is very important to define the concept of thermal equilibrium. But by this time, too many books were already written with the statements of first law and second law of thermodynamics. So it was not possible to change the numbers that were given earlier. So the scientist Fowler was forced to adopt 0 as the number for his law, and so this law came into existence, that is the zeroth law of thermodynamics. So this was the history why this name zeroth law of thermodynamics was given. This zeroth law is the fundamental law of thermodynamics. So it was necessary to put this law before or prior to the first and second law of thermodynamics. Hence the name zeroth law of thermodynamics. Now we will see what is the statement of zeroth law of thermodynamics. So this law states that if two thermodynamic systems are each in thermal equilibrium with the third one, then they are also in thermal equilibrium with each other. So let us understand this with the example or the diagram that is given below. We will assume three systems which are given as follows, that is system A, B and C. Now if we place system A and system C, if they are in thermal equilibrium, we have already studied what is thermal equilibrium in previous lectures, that is temperature of both the systems should be same. Okay, so if system A and C are in thermal equilibrium, and again if we say that the systems A and B are also in thermal equilibrium, then we can say that the remaining two systems, that is the system B and C, are also in thermal equilibrium. I will repeat this concept once again in addition with the concept of thermal equilibrium. We have considered three systems, that is system A, B and C. So if we are bringing the two systems, that is system A and C, in good contact with each other, then what will happen? We have already studied that in case of thermal equilibrium, the energy in the form of heat, it will transfer from a body at higher temperature to a body at lower temperature, and after some time the temperature of both the systems will be same. So this is nothing but the thermal equilibrium. So if we bring A and C system close to each other or in good contact with each other, then the temperature of both that systems will be same. Now again if we bring the other two systems, that is system A and B, in contact with each other, then again the thermal equilibrium will be achieved. So based on these first two conditions, we can now say that the system B and C are also in thermal equilibrium. So this is the zeroth law of thermodynamics. If still you have doubts, then we can understand this zeroth law with the help of one more example. I will explain that in further slide. So just like previous example, we will consider three systems, that is system A, B and C. So system A is nothing but ice which is at 0 degrees Celsius. System B is nothing but a glass of hot coffee. We will assume its temperature say about 60 degrees Celsius. And our third system, that is system C, will be nothing but the surrounding atmosphere where this cup of hot coffee is placed. Now if we bring the two systems together, that is system A and system B, if we bring these two systems in good contact with each other, then what we will do, we will put that ice into the glass of hot coffee. So this means that we are bringing these two systems in good contact with each other. So after doing this, the ice will start to melt because the hot coffee is at temperature 60 degrees Celsius and the temperature of ice was 0 degrees Celsius. So thus the ice will start to melt, or we can say that the temperature of ice will start to increase, whereas the temperature of that hot coffee will start to decrease. So this process or the transfer of heat in between these two systems will continue until both the systems are at same temperature, that is the condition of thermal equilibrium is attained. So now we will have a new system of this mixture, and if we assume that the temperature of this system is about 30 degrees Celsius, and on the other hand, if the temperature of our third system, that is system C, is about 25 degrees Celsius, that is the temperature of the surrounding atmosphere, then again heat will start to travel from this mixture to the atmosphere, because the mixture temperature is 30 degrees Celsius and the surrounding temperature is 25 degrees Celsius. So again the heat will start to travel from high temperature to lower temperature region, that is from the new system which is obtained by the mixture of ice and hot coffee to the surrounding air. So in this way, the heat will go on transferring, or it will go on traveling unless a stable condition, that is thermal equilibrium state, is obtained. So I hope that with this example you might have now understood the concept of zeroth law of thermodynamics. Now we will see the law of conservation of energy. First we will see the statement for this law. It states that energy can neither be created nor be destroyed. Although it may be transformed from one form to another, the total amount of energy in the universe remains constant. So according to this energy, we can understand that any kind of energy cannot be destroyed nor it can be created. We are just converting one form of energy into another. If we consider example of a car, then in car we are actually providing chemical energy in the form of petrol or diesel, and this fuel or chemical energy is actually converted into mechanical work. Similarly, if we consider another example, say electric lamp, so when electric supply is provided to the lamp, then this electrical energy is converted into light energy. So in this way, we are not creating any energy nor we are destroying. We are just converting one form of energy into another. So this is given in the law of conservation of energy. As shown in diagram, we can see that a vehicle is at top position. So when the vehicle is at top position, at that time, it will have higher amount of it will have higher amount of potential energy, whereas at the same time the kinetic energy is minimum. When this car comes down, then at that time the potential energy is converted into kinetic energy. So here, as the vehicle comes down, the kinetic energy will be maximum and the potential energy will be minimum. So this is all about the law of conservation of energy. We will now represent this law in mathematical equation. So we know that the amount of energy in any system is determined by the following equation, that is ut is equal to ui plus w plus q. Ut is the total energy of the system, ui is the internal energy of the system, that is a summation of kinetic energy and potential energy. Q is the heat added to the system or heat removed from the system, and W is the work done by or on the system. So the change in internal energy of the system can be determined by the following equation. Delta U is equal to W plus Q. First law of thermodynamics. It is actually the modified version of law of conservation of energy. This law gives a relationship between heat and work. So this relationship can be stated in three different ways, which are given below. So the first statement is when a closed system undergoes a cyclic process, then the sum of heat interactions is equal to the sum of work interaction. So this entire statement we can mathematically write it as follows. Summation of Q is equal to summation of work. That is the total summation of heat is equal to total summation of work for a cyclic process. The second statement is for a cyclic process, heat and work are mutually convertible. For example, engine. So if we consider the engine of a two-wheeler or four-wheeler, then in that engine we are actually providing the chemical energy of fuel, which is first converted into heat energy, and later on this heat energy is converted into mechanical work. Likewise, in many other devices we can also convert work into heat. For example, electric iron or electric heater, where we are supplying the electrical energy, which is nothing but the outcome of mechanical work. So in case of electric heaters, the input work in the form of electrical energy is converted into heat energy. So we will see the next statement for first law of thermodynamics. The third statement is the change in internal energy is equal to the difference of the heat transfer into the system and work done by the system. So mathematically we can write this statement as follows. Delta U is equal to Q minus W, where delta U is change in internal energy, Q is heat added to the system, whereas W is work done by the system. From this equation, it is clear that if we are adding heat to the system, then it will add to the internal energy, whereas if work is done by the system, then it will reduce the internal energy of the system. Let us understand this with the help of the given diagram. So here we can see in the diagram that a container which is filled with certain amount of gas is given. So this is nothing but our system, and on this system or in the container, piston is placed on this gas. Now if we heat the system, that is if we heat the gas molecules, then initially the gas molecule will start absorbing that heat, and with further addition of heat these gas molecules will expand. As a result of this, the piston will be forced to move in upward direction. So we can say that work is done by the system on the piston. On the other hand, if we remove heat from the system, then again the gas will contract, and as a result of this, the piston will exert some force, or it will move in downward direction. So from this we can understand that whenever there is the exchange of heat and work in between system and surrounding, there will be always a change in internal energy. So this is all about first law of thermodynamics. We will also see what are the limitations of first law of thermodynamics. So the first law of thermodynamics does not give any information regarding the direction of heat and work transfer. It also does not tell whether the system will undergo change or not. And the third limitation is it does not give any information regarding how much amount or how much percentage of one form of energy is converted into another form of energy. So these are the limitations of first law of thermodynamics. There is one more concept related to the first law of thermodynamics, that is PMM1. We call it as perpetual motion machine of first kind. So a perpetual motion machine of first kind is a device or machine that violates first law of thermodynamics. Such a machine will give continuous work without receiving energy from other system, As in first law of thermodynamics, we have already studied that heat and work are mutually convertible. We are converting the heat energy into work, or vice versa. That is, we can convert work into heat. But the perpetual motion machine is a machine which is going to give continuously output work without consuming any kind of energy. So such kind of machine is practically not possible. So it is never possible to construct such type of machine. As in the previous lecture, I have told that in this lecture I am going to share the important questions which have been asked from MSBT. So these are the three questions from second, third, and today's lecture, which are asked in the previous three MSBT papers. So the first question is, explain the concept of flow work associated with flow process. This question was asked for 4 marks in winter 19 paper. The second question is, differentiate between heat and work, and this question was asked for 2 marks in the paper summer 19. The third question, it was asked for 2 marks in winter 18, definitions for flow work and entropy. So these are the questions from previous 3 papers based on our past 3 lectures. In the next lecture, we will start with a new point, that is second law of thermodynamics. So till then, you should revise all the points which we have discussed up till now. So thank you.